Hello everyone. Today I'm going to talk about decision tree classifiers. I will cover everything from loading and preparing the data, building the model, visualizing the tree, evaluating performance with different metrics, and even tuning hyperparameters to improve results. So let's get started. We start by loading our dataset. This is a heart disease dataset from a Kaggle website. Each row represents a patient with features like cholesterol, blood pressure, age, and more. The target column here is C, which indicates whether heart disease is present or not, with 1 and 0. In supervised learning, C is our dependent variable. We have to define for Python which one is our dependent and which one is our independent variables. So here x contains all the features used for prediction, and y is the target variable we want to predict. A axis is equal 1. It means we are dropping columns, not a row. So we replace missing values with 0. This is a quick for this example, but in real world cases, we have to use mean median imputation, Cannon imputation, predictive models for missing data, which I explained these methods in my previous video available in my channel. Here we split the data. Sometimes researchers split data into three parts: train, test, validation. This can be useful in semi-supervised cases where some target values are missing. In such cases, you can train on the available labeled data for 80% for training and validate on a part of it, and later test on the remaining data. So here we have 80% training and 20% for testing, and random states is equal to 72, and you can choose any number, and it's for ensures reproducibility. So the golden number for this that most researchers use is 42. So if we want to print X-train and test, as you can see, the training set is 477 rows, and testing is 120 rows. So the sum of this can be 597, same as the original datasets, with 13 features for training. So, as like before, we spoke about the initialize, fit, and test. We use here for that method for that three steps. Now, fit is trains a model on the training data and predict makes prediction on the test sets. Uh, but here we don't have prediction. A decision tree works by splitting the data at each node based on a condition until the groups become pure. So from the 80% training data, we build a model that learns how to predict the target. How does it learn? It depends on the algorithm we choose. We have different kinds of algorithms that AI-based like neural networks, tree-based like decision tree, random forest, and statistical or probabilistic. Here, our model learns patterns to predict 0 or 1, positive or negative. So we then evaluate the model using the 20% test data by comparing the predicted results with the actual results. These three steps modeling process train, predict, and evaluate is the same in deep learning and big data also. This quickly gives the accuracy score. Now that we have our model's predictions, let's check how well it's actually performing. We have different kinds of metrics in scikit-learn. Accuracy tells us out of all predictions we made, how many were corrected overall. Recall focuses only on the actual positive cases. For example, people who truly have heart disease and asks how many of them did our model correctly find. Precision flips the question. It looks at all the cases where our model predicted heart disease and asks how many of those predictions were actually corrected. And F1 score combines precision and recall into a single number, which is useful when you want to balance both. And a confusion matrix is like a scoreboard that breaks predictions down into four categories: true positive, true negative, false positive, false negatives. And in the next, let's visualize the decision tree itself. So we can see how it's splitting the data. From scikit-learn, we use the tree subpackages and import the plot tree. Here is what's happening. I set maxib equal to 2, so the tree stays small and readable for demonstration. Fillet is equal to true, and the colors each node based on the predicted class. And keeping trees shallow like this can also help prevent overfitting because very deep trees can memorize the training data instead of learning general patterns. When working with decision trees, there are a few key parameters we should know how to tune. The first criterion, it tells the model how to measure the quality of split. The common choices are Gini or entropy. Next step limits how deep the tree can grow. Here you can see we have 0, 1, and 2 depths. We choose 2, and usually we try values between 2 and 15 to see what works best. Mean sample split is the minimum number of samples needed before a node can split into branches, and mean samples leave the minimum number of samples that must be in each final leaf node. And the class weight is very useful for imbalanced datasets. Setting it to balance it automatically adjusts the weights of each class, or you can assign your own manually based on experience, but it needs to have more and a clear experience about the dataset to choose your own manually. Now we can compare train and test. I used 4, and for each eye in range 1 to HP max, we do the 3 steps. This is the same eye number for each time for decision tree. So then for append the eye, it asks 3 things. One, the number of tree depth in eye. Second, terrain score. And third, validation score. So now we can compare terrain score with validation. When looking at this plot, the best depth is usually where both training and testing curves are high and close to each other. If the training accuracy is much higher than the testing accuracy, that's sign of overfitting. So thank you for watching this video, and we explained how to load and prepare the dataset, train and visualize the decision tree, evaluated it using accuracy, recall, precision, the fun score, and the confusion matrix. And we looked at the key hypermeters you can tune, find the optimal depth by comparing training and testing performance. Thank you.